To prove the approximation factor of this improved algorithm, we need first some lemma, which is the so-called structure lemma. The structure lemma tells us if we look at a single iteration of the algorithm and the set of connected components that we have in it, but only those that contain exactly one terminal of a terminal pair, then the number of edges in the solution that we have that lie on the boundary of these components is at most 2 times the number of the components. If you remember, that was exactly the approximation factor that we got from our previous version, from the naive Primal-Dual. And there we show that this can be k, but now we can show that we get to a factor of 2. So we want to show that for all these components that we currently have in the current iteration of the algorithm, there are on average at most 2 outgoing edges in the solution we compute at the end. And intuitively, there has to be at least one edge of those, because we still have to connect the terminal pair, so at least one of them has to be in the solution. If we show at most 2 are there on average, then we basically have a true approximation. But that we'll come to later. Let's try to prove this first. First about the intuition. So we look at the current step of the algorithm and we have computed some connected components like this. Now there are different type of edges in the graph. There are some edges that are inside a component and that will be in the output at the end. Those are the brown edges here. Then there are some edges that we pick but that we remove in the pruning later. Those are the green dashed edges. And then the important edges for us that are those that are on the boundary of a component and also in the output of our solution. Those are the cyan dotted edges. And we want to count how many of these do we have. And the intuition is that every component of the subgraph of the edges that we compute before the pruning gives us a forest in f prime. So for every component we have a forest, and the average degree of a forest is at most 2. If I look at all the components here, then we can argue that the number of edges of these type that we have is at most 2 times the number of components. The problem is we don't look at all of them. We only look at the components that contain exactly one terminal of a terminal pair. So in the worst case it could be that only this component here has a terminal of a terminal pair and the other ones don't. This is of course not realistic, there has to be a second one, but just for the argument, this one here has basically degree 3. There are 3 edges that go out of this component. So if I only count this one, then the argument doesn't hold, it needs all the others. So we have to be a bit smarter in arguing that exactly these components that we have at most 2 outgoing edges in f prime on average. So let's try to prove this. We want to look at the ith iteration where the edge ei is added to our set f. I want to define 2 graphs. The first one is I want to look at only the edges that we've picked so far. That's the set fi, the edges e1 to ei. If we look at the graph gi that contains only these edges, then there's this graph here. And here, all the connected components that we have, that we need later. So these are the brown ones. And then we also have the graph gi star. This is the same one, but here we also add the edges that will be added later and that are in f prime. We don't add the edges that will be added later, but then pruned again. Now what we want to do is, we want to take this graph here, and we want to contract all the components of gi, so all the brown components here, to a single vertex. And this gives us a graph gi prime that looks like this. So I have this vertex that corresponds to this brown component, this vertex that corresponds to this, and so on. And we have an edge between each pair of vertices here if there's an edge between their corresponding components in gi star. So basically we have these edges here that correspond to edges in f prime that are not yet picked. And now this graph here is a forest. Why is this the case? I mean, in general, the graph that we get in the end is a forest, so we add only forest edges. But, as you can see here, this is the component, but this edge is not inside. So it could be that we prune this edge, and then we have another edge here, and then the whole thing is still a forest. But because we do the pruning backwards, if we would have another edge here that creates a cycle, then this was added later. And that means that this would be pruned before this one. And then that's a contradiction. So this one cannot be inside if this one is not in it. So we cannot get any cycle in this graph Gi prime. And the same way we can also argue that we don't have any multi-edges. So theoretically it could be that there are like 4 extras, for example, between this component and this component. But then why would we have these 4 edges? It's only because some edges inside will be pruned. If we don't prune any edges inside, then we will have a cycle. But these edges cannot be pruned if we have later ones that make a cycle, because the later ones will be pruned before. So again, we cannot have any multi-edges, we cannot have any cycles, so this has to be a forest. So that means if we look at all the components we have in this graph and we count how many edges of f prime are at the boundary of those components, then that's exactly the sum of the degrees of the vertices in this graph. Because for all of these edges we have an edge here. And summing up all the degrees, we get exactly twice the number of edges because we count every edge twice from its endpoints. And since this is the forest, if it has n vertices, it has at most n minus 1 edges. So the number of edges is at most the number of vertices. This is even strictly less than, but doesn't matter. And this is basically this inequality, except that we still don't have this part that we only consider the components that are in our set C. This is for all components, the sum of the edges in f prime on the boundary is at most 2 times the number of all components. So we further have to distinguish here. And now we will mark some of these vertices as active and inactive. Oh, look at this here. We have in this component some terminal, and in this the corresponding terminal of the pair. So these 2 components we still have to connect. Then we mark them as active. Also these 2 we still have to connect, we mark these as active. And this component here, it doesn't have a single terminal of any terminal pair, so this is an inactive one. This one we don't have to connect to anyone else. It might still be connected as here, but only because others find their way over this component. And now the active components are exactly those that are in our set C. Those are exactly the components where we have exactly one terminal of some terminal pair. So we only have to count for these active ones how many edges of f prime do we have at their boundary. And to do that we look at it the other way. We look at the inactive ones. Now I want to figure out how many edges must these inactive ones have on their boundary. And in fact they must have degree at least 2. Why is that the case? If they have degree 0, then they are not in this graph. This one here has degree 0, it doesn't have any others. Those we completely removed. Those don't exist. So it cannot have degree 0. If it has degree 1, then that means it gets connected to some other component. But why would we connect it to some other component? Because it doesn't have to connect somewhere else. There is no single terminal that has to be connected to another one. So this edge that we would add to another component, that we don't need, that doesn't give us anything, that would be removed. So the only way that this is in the graph is if it has degree at least 2. For example here, this component connects to it, and then there's another one that connects to this component, such that we can connect these 2 terminals. So the red vertices, the inactive ones, have degree at least 2. So this here is exactly the sum of the degree of all active components. The sum of the degree of all components is 2 times the number of vertices. The inactive ones each contribute at least 2. So the sum of the degrees of the active ones is at most the total sum minus 2 times the number of inactive ones. So we have 2 times number of vertices minus inactive ones, so 2 times number of active ones. And the active vertices are exactly our set C, so this is exactly 2 times the size of this set. And this proves the structure lemma.